Hi, I'm Steve Ward, and I'm going to give you an introduction of electronics, particularly as they're applied to programmable logic controllers or PLCs and industrial PCs. So let's start with the basics of electronics, which is around electricity and the concepts of voltage, current, resistance and watts. So electricity, at a physical layer, it's actually the flow of electrons through a conductor. So there's underlying physics, and you can explore the underlying physics in more detail if you need to, but you don't need to understand the actual physics of the electrons in order to be able to understand how the electronics part works. So we start with voltage. Voltage is effectively the pressure of the flow, and we measure that in volts. So higher volts means more pressure, lower volts means less pressure. Voltage is also something that can overcome resistance. We'll talk about that in a minute. So higher voltages, we also have to be a bit careful because they can be dangerous, whereas lower voltages with less flow, they aren't as dangerous. And I'll talk a bit about electrical safety later. Now, although we have a pressure of flow, that doesn't mean there is actually any flow. So we measure the amount of flow in terms of current. So current is the actual number of electrons which are flowing through the conductor. And we either measure that in amps or in milliamps. So amps is A, but amps is quite a high value. So for many applications, we're more concerned with milliamps. So a milliamp is a thousandth of an amp. And of course, multiple milliamps is fractions of an amp. That's different from volts. Volts we normally measure just in volts. Unless we're measuring very low level signals, we just measure volts at an integer level. Now, what controls the amount of flow through the conductor is how much the resistance there is. Resistance is effectively how much the current is pushed back on and how it's prevented from flowing through the conductor. And we measure that in ohms. Again, typically with ohms, unless we have very fine systems, normally ohms are measured as integer values. And sometimes in high levels of ohms, we're not even measuring in ones, but we might be measuring in tens, hundreds and thousands, and even tens of thousands of ohms. Now, when electrons are going through the conductor, they are performing work and there is energy produced. That energy can either be measured as, for example, rotational energy in a motor application, or it might be measured as heat. If we have a heater element, heat can also be waste energy that's not used in the system. Watts can also be measured as the amount of light produced, for example, by a lamp or an LED. And in practice, it could be a combination of 2 or 3 of those, because whenever you generate some sort of power, there is also some wasted power as well. So watts is the work done or the energy produced, including that wasted energy, which we might also be interested in. And watts is typically measured in individual watts, but for large applications we might measure it as kilowatts, or in very, very large applications, maybe even megawatts, but not normally in PLC systems. So those are the basics: voltage, current, resistance, and energy or watts. So a good analogy for voltage, current and resistance is using water flowing through a pipe. So you have a tap, you turn on the tap, water flows through and water comes out, and between the tap and the main source and between maybe the outflow there is a pipe. So effectively what we're doing is we're imagining that flow of water through a pipe, and we can use that to understand how electricity works. So voltage is the pressure of the water flow. So if you've got a very large tank or it's very high up and you've got gravity pulling the water down through the pipe, that gives you your pressure. So that's the equivalent of voltage. Current is the volume of the flow of water. So if you've got your tap, then of course if the tap is closed, there's no current. So the pressure is still high, but the current is 0. And as you open the tap, the current starts to flow, the water starts to flow. So that's your volume of flow of water through the pipe. And resistance, that's how much the water flow is restricted by the width of a pipe. So a larger pipe can carry more water, so lower resistance, and a smaller pipe can carry less water, so that's higher resistance. So a great analogy of imagining water in terms of, or imagining electricity in terms of that water flowing through that pipe. Now, a note about direct current or DC. versus alternating current or AC. DC is generally used in lower voltage circuits, and in larger applications where we need more power, we use alternating current. So for example, mains power is typically AC coming from the mains supply, but when we're talking about lower voltages in PLC systems, they're often DC or direct current. Industrial applications often combine both DC and AC. So AC, that's where your higher power or higher voltage applications work. So again, mains power or possibly motors, they typically use AC. And it's quite easy to convert AC voltages from one voltage to another by using a transformer. What happens in a transformer is the voltage is flowing first one way, then another way, typically in a sine wave over a particular period of time. And that transformer, using electromagnetic conductance, that can be used to convert those voltages. DC means that the electrons travel in a single direction, and typically it's a constant voltage, and that means then that you have to use more electronics to actually convert the voltages from one voltage to another, because you haven't got this capability of using the simple electromagnetic function. You would use an electronic function instead. Now AC means that the electrons are traveling in alternate directions. That means that usually it's a sine wave. So we have to consider that we have a sine wave, we have a peak voltage, but we typically measure the AC voltage using the root mean square voltage. So if you were to put an oscilloscope on an AC voltage, if you were to put that on a main supply of 230 volts, you'd actually see there's a peak of 262 volts, but the nominal 230 volts is the root mean square. And the way we calculate this, we look at the RMS voltage and we calculate that as 0.707 of the peak. Or we can do it the other way around. We can calculate the peak voltage based on the RMS, which is 1.414 times the RMS voltage to get the peak voltage. So the way this works is if you were to use an oscilloscope, you would see the sine wave and you would see the crossing wave going across 0 and up to the peak voltage. But if you were to use like a multimeter, the multimeter averages the voltage and it gives you the root mean square value. So again, just need to be careful of that, because there are some devices which are triggered at a certain voltage. You may have a nominal AC voltage which is lower than the trigger of the value, but a peak voltage may actually cause that device to shut down. For example, we have a certain voltage operated type resistors, and if you go above that peak value, you can actually trigger that even though the nominal voltage might be okay. But relatively straightforward. Direct current is typically used in lower voltage and lower current applications, and we use alternating current in bigger, larger applications where we need more power. And here's what the AC voltage looks like. AC has two components. It has the voltage, of course, but it also has frequency. So in most of Europe, for example, AC generators produce electricity in a sine wave pattern. You might see sometimes the sine wave isn't a true sine wave. That can be caused by harmonics and disturbance on the waveform, but generally it should be a pure sine wave like this. So in Europe, the frequency is 50 Hertz. So each cycle from the start through the maximum voltage, through 0 to the minimum voltage and then back to 0, each cycle is 20 milliseconds. In the USA, the frequency is 60 Hertz, which means each cycle is 16.67 milliseconds. So it's a bit faster. And there's not really a problem about what the frequency is. You just have to be aware of it, because some electronics does take into account the frequency. And also you might want to filter the frequency out of a DC circuit. So knowing what the frequency is can be important for your filter to work correctly based on that frequency of the source supply. But as I say, it's a sine wave pattern. Notice again the peak voltage, and you also have to consider the RMS voltage, which is about 0.7 of the peak voltage. Or alternatively, if you know the RMS, it's 1.4 times the RMS value is your peak value. So let's move on to more basics of electronics. I'm mainly going to be working as if we're talking about DC voltages, which is what we usually encounter in modern PLC systems and definitely in industrial PCs. If it's AC, then I'll mention that separately, but normally we're talking about DC voltages. So in terms of the electronic basics, we have resistance, and another component of those is voltage and current. And voltage, current and resistance are related to each other. So we start with, on the left, we have the voltage, which if you remember is your pressure of your energy coming in. So you have your voltage. The actual flow through the resistor is your current. So you have the voltage, the current, and the resistance. And then another component of that is the work performed, or the energy, which is measured in watts. Other common electronic devices we come across: capacitors. Capacitors store energy. They're often used to filter DC voltages, because a capacitor, depending on the size of the capacitor, allows AC voltages through but blocks DC voltage. We have inductors. Again, they store energy but in a slightly different way. In PLCs, inductors are often used to filter AC voltages, because what the inductor does is it passes DC but it blocks AC. So it's like the opposite of a capacitor. They both store energy, but one filters DC, capacitor filters DC, and in the inductor filters AC. And then in a typical electronic device, we have a multitude of different types of semiconductor device. So first of all, we have a diode. A diode is an electronic semiconductor device that limits current flow to a single direction. You can have transistors, which are electronic switches. They can switch a larger current based on a small current. And then we get integrated circuits, or ICs, and these combine multiple diodes, transistors, and possibly even resistors and other components into a single package. And they can be very, very complex, all the way up to, for example, a computer CPU, which can combine millions of transistors into a single small package that's maybe just the size of your thumbnail. So let's take a look at diodes. Most diodes are made from silicon, and they have two different layers of silicon with slightly different properties joined to each other. And when you connect those to each other, you create the diode. And the diode is a particular function where it allows electricity flow in one direction but not the other direction. So it's very often used for reverse polarity protection. So if you have a DC voltage, if you have 24 volts coming in going down to 0 volts, some electronics would be fine with that, but they wouldn't be fine if you reverse the polarity. So what you could use in your electronic circuit, you could use a diode which would block the DC voltage in the opposite direction. When you're switching inductive loads, there's also a property when the induction collapses, then you get a high reverse, what we call an EMF, an electromagnetic field, which creates a high voltage. And that can cause problems with electronic circuits. So diodes are often used on the output of an electronic device when we're switching inductive loads to absorb that back EMF and absorb that high voltage. Now with diodes, there's typically a small volt drop because of the way the silicon works. And with a standard silicon diode, it's 0.7 volts. There are some other different materials we can use which might have different volt drops. So if you look at your symbol for your diode, this is what the diode symbol looks like. It's a wire, and then it's a sort of triangle with a line against it, and that symbol means that you have a diode. Current flow is in the left to right direction through the diode, so it comes in on the triangle side and goes out on the bar side. There would be a volt drop across the diode in that direction, but in the other direction, current wouldn't be able to flow. So the semiconductor would block any energy flow going from right to left, up to a limit anyway, depending on the diode. For example, a typical diode might have 1000 volts breakdown voltage. If you put over 1000 volts across it in the wrong direction, then that would overwhelm the semiconductor physics electronically and mechanically and electrically, and the voltage would then be able to cross. That would probably result in catastrophic failure of the diode, and then it would no longer be a diode. It would just act either as an open circuit if it had completely failed, or it might go short circuit and just allow voltage through. But in normal use, you're only allowed to have voltage from left to right with a small volt drop, and no voltage or current flow from right to left when it's aligned like this. So a bit more about inductive load behavior. Inductive loads are generally coils, and we often see those in relays and other sorts of actuators. So that might be a solenoid to control a pneumatic valve. It might be a contactor, which is a larger version of a relay. What happens is when the coil is energized by a DC output, a magnetic field is created, and that lasts as long as the output is on. So we're energizing the coil, The coil is then doing what it needs to, using electromagnetic functions to control what the output is, for example, operating the relay contacts or driving the solenoid or so on. While that's going on, the magnetic field is present, but what happens is when the output is removed, that magnetic field collapses, and because we have a relationship between electricity and magnetism, when the magnetic field collapses, that causes a reverse voltage to be created. That's called a back EMF. And that back EMF can be quite high. You might have a 24 volt coil, which is normally running with that magnetic field and everything is fine. But when the magnetic field collapses, the reverse EMS could be much higher than that 24 volts you're supplying it with. It could be 24, it could be 50, it could be 100 volts, depending on how big the coil is and how quickly that magnetic field collapses. So there's also a relationship with resistance, there's a relationship with capacitance as well, but often the inductive load overwhelms those other characteristics. So we have to be careful of that back EMF, because if that was applied directly to a solenoid output, like a transistor or some other semiconductor device, potentially that reverse voltage could overwhelm the device and cause it to fail. So that's where the diode comes in the previous slide. You're having a high voltage diode wired to stop that back EMF, that effectively protects your output. Now there is a type of diode that allows current flow in both directions. This is called a Zener diode. It still has that small volt drop in the forward direction, and what it has is a controlled breakdown voltage in the reverse direction. There's Zener diodes available with a variety of voltages, and these are very good for voltage limiting applications. So here's your symbol for a Zener diode. You've got that same triangle and the bar as before, but now you've got two little other bars at the top and bottom of the diode output. So that's the symbol for a Zener diode. In normal conditions, you get current flow in the direction from left to right with your small volt drop. But in the reverse direction, there would be no current flow until you reach the breakdown voltage, and then current would flow. So if you wanted to make sure that the output of a circuit was limited to 24 volts, you could get a Zener diode rated at 24 volts, mount it in parallel with your circuit, and then what would happen is, under normal circumstances, there would be overall current flow to your device. But if the voltage went above 24 volts, it would then flow through the Zener diode, and that would prevent getting a higher voltage on the output. Now, we don't tend to use these too often, but they can be used for protection of circuits which are sensitive to high voltages. They're often used for that. You just need to be careful that, of course, what is the current flow? When you have a current flow going through a Zener diode, it's effectively acting as more or less a short circuit in the reverse direction. So you need to be careful of, are you overloading whatever your original output circuit is? So can be used, but there are some sort of rules and guidelines about where or why you might use them. But I do see these quite often in applications where we want to limit the voltage and make sure that we're not overloading something that's sensitive to high voltages. So this brings us to transistors. So a transistor is another semiconductor device. This time, instead of having two semiconductor layers, we now have three semiconductor layers. And these are arranged either as NPN or PNP. You can use different types of semiconductor. Typically there's a silicon. But the way it works is, by using your different levels of silicon, you can effectively create a switch. So what happens is, under normal circumstances, you have your collector, if this is an NPN resistor or an NPN transistor, your collector is connected to your high voltage. The base is the input signal, if you like. And then what happens is you have an output on the emitter, and when the base voltage comes on, that enables current flow through the collector to the emitter. So if there's nothing on the base, it effectively acts as an off. So it's like a diode in the reverse polarity. But if you turn it on by putting a voltage on the base side, then it effectively creates a short circuit between the collector and the emitter. It's not a full short circuit. There's still a little volt drop, and that depends on the materials that are used. So what we have is, with a transistor, it allows us to electronically switch a larger current from a smaller current. When the base turns on, that turns the transistor on, and then current passes from the collector to the emitter. Now, NPN is the most common type, where we have a collector and the emitter goes to the load. So we have our NPN, that's used in what we call positive logic, and that sources the current from the collector to the load. PNP is also possible. This switches in the reverse direction. So with PNP, the base is a low signal to turn on the transistor. So it's the opposite of what you would thought. You turn it off and the energy turns on, whereas NPN is positive logic. You turn it on and you get current flow as you would expect. It's also about sourcing and sinking of current. So an NPN can be considered as sourcing from the collector to the load via the emitter, whereas often what happens with a PNP, it's wired with the load is on the emitter, the base is wired to our control circuit, and then the collector would effectively be 0 volts. So we're sinking current from the load through the transistor and down into ground. So these are the symbols. You see you have a circle, and then inside you have a line with the base on the left hand side, and then you have your collector is a single line, and your emitter, that's the line with the arrow on. So with NPN, the emitter is at the bottom. With PNP, the emitter's at the top. So it's effectively an electronic switch. We have a circuit between the collector and the emitter, and it turns on when the base is turned on, or if it's a PNP transistor, it would turn off. Now, these can be used as switches. In some older circuits, they're also used as amplifiers. So if you had an electronic system like an amplifier, if you're playing music, for example, there would be transistors inside your amplifier which are used to actually amplify the signal. So you could have a low voltage coming from your pickup on whatever your device is. That might be an electromagnetic pickup. Think of a record player where you've got your diamond on a small short stylus which goes to an electromagnetic pickup device. That would be a very low voltage which goes through a series of transistors to be magnified or amplified. But in PLC terms, we're not normally concerned with variable voltages. We normally just use it to turn on or off. Now, there is a concept of the amount of amplification. A typical transistor will magnify by 10 times. So, for example, if you want to control a current of the collector to the emitter of 1 amp, then you would normally need a 100 milliamp supply on the base side. But some transistors can magnify more than that. You could get transistors with an amplification factor of 100. And it's also possible to cascade resistors or transistors together. So you could have 2 10 times together to make 100 times and so on. So the actual situation might be a bit more complex than this. But at basic level, this is how we control it. So it's a simple switch by controlling the base, and that controls the flow between the collector and the emitter. Now, transistors are built into larger semiconductor devices, and from these we can create binary devices. So we can create something that inverts a signal, a NOT gate. We can create AND gates. We can create OR gates. We can create other types of gate. That's really beyond the scope of this overview. That's more where we start getting into logic circuits. I'm going to be focusing more on the actual electricity and electronic side for controlling inputs and outputs. So in the PLC, we're often starting with quite low voltages. Inside the actual CPU, the voltages might be down to 1 or so volts. Typical electronics, you have a 5 volt is what's used for traditional what we call TTL logic, which is transistor logic. More recently, we have designs based on CMOS technology, which uses lower voltages. And modern CPUs inside the CPU itself can be a very low voltage, as I say, down to just over a volt or so. In the real world, having a 1 volt signal is not very much use. Even 5 volts is probably too small for us, because 5 volts might be enough to operate something, but it wouldn't be enough in terms of the size of voltage. It would mean we'd have to have a very big current, we'd need very big conductors and so on. So we tend to avoid those lower voltages and we use larger voltages. So what we need devices which can effectively amplify that voltage. And one option is to use an electromagnetic component called a relay. So a relay uses a coil to generate a magnetic field to switch a contact or set of contacts. That's commonly used for interfacing purposes where we don't have very high currents. And the idea is the relay, they can be very small, down from the size of almost like a thumbnail, and they can be up to quite large devices, including pluggable devices. And it depends on how many contacts you've got and how much current you want to switch. But a typical relay would take a 24-volt output from a PLC, and then that will turn that into a contact that we could use to switch, say, a 230-volt device or maybe a 110-volt AC device. Now, a contactor is very similar to a relay, but this can be used to switch much larger currents. So on the contacts output side, the contactor has larger contacts which can switch more current, and that's often used to control bigger devices. So maybe three-phase motors, where you might be looking at much higher numbers of amps, or other large electrical devices which have very high power. So physically, a contactor is normally larger than a relay because inside, first of all, the contacts have to be a bit larger. Also, because the contacts are larger, there's more mechanical load, so the coil has to be a bit larger as well. But otherwise, a relay and a contactor, they're very similar in the way they operate. They're just different in terms of the size and the sorts of applications they're used for. Now, we can also have solenoids. A solenoid is a coil that generates a magnetic field to drive a physical component. For example, you might be driving a pneumatic valve. So pneumatic valve, you're operating an internal flap which diverts the pneumatic pressure in one direction or the other, and that's driven from the solenoid, which again uses that same sort of electromagnetic technology based on the coil, and that coil can be driven from a voltage from the PLC. And depending on the voltage of that coil, that's where a relay might come in to magnify a smaller voltage into a larger voltage to actually make sure we've got enough voltage to drive that solenoid. Another very common electromagnetic component is a motor. A motor uses multiple coils that generate magnetic fields to drive a rotary shaft. There are lots of different motor types. I've got a separate slide deck on that. But typically you'd have several coils which are driven from an AC voltage, and based on the AC voltage coming in, that would drive one coil. Then as the AC voltage changes, that would drive another coil. Then as the AC voltage changes, that would drive another coil. And the coils are arranged so that the electromagnetic effect is circulating in a circular fashion around the motor. And then the motor drive shaft, that would either have permanent magnets on, or the magnets might be on the actual outside of the motor, depending on what sort of motor it is. But the idea is you would drive the electromagnetic effect so that the motor shaft is pushed around by that rotating electrical and magnetic field. So that drives the motor based on the electricity coming in. So multiple different motor types, and they can operate in lots of different ways. So I won't go into those in too much detail here. Generally, the motor itself is driven by the concept of the AC electricity, and we don't have to be concerned to it from a PLC point of view, but we might need to understand a bit more if we're getting into variable frequency drive technology. There are also linear motors. This uses the same technique with multiple coils, but instead of being in a rotary orientation, they're in a flat orientation. And typically with a linear motor, you're either driving something from one end of a slide to another and then back again. So that can be used to replace a pneumatic coil and gives us better control and maybe more power. But otherwise, very similar to a motor in the way it operates. It's a combination of interacting AC voltages along with another device which could either be a permanent magnet or another set of coils driven through a different mechanism. So we've talked a bit about voltages. Let's go into a bit more detail about voltages as they apply to a typical PLC. Now today, most industrial devices use 24-volt DC. 24-volt DC is relatively low. It's considered safe to touch. And what we do is to get the 24-volt DC, we obtain it from mains voltages via a power supply, or PSU for short. A big benefit of 24-volt DC, it is relatively safe. It's high enough that we get power to operate most standard devices, but it's not so high that we need a lot of insulation. And depending on the sort of current we need, the wires that we use to handle 24-volt DC, they're easy to use when we're building a panel or a cabinet, and they're quite easy to manipulate between multiple different devices. So safe to touch and easy to obtain. There are some devices which use lower voltage. 5-volt DC used to be common for encoders, for example. An encoder is a device that measures rotational position, typically from a motor shaft or a gearbox shaft. But even now, we see those as being more commonly used with 24-volt DC. Another good reason for 24-volt DC is, it's relatively immune to noise. Because we've got that higher voltage, if you had electromagnetic interference on a 24-volt DC wire, yes, you would be able to measure it, but it probably wouldn't affect the 24-volt DC circuit. Whereas when you've got lower voltages like 5-volt DC, it's possible that would be affected by electromagnetic interference, and that would cause a misread of the encoder device, for example. So again, that's why a lot of encoders now are switching to 24 volts. Having said that, we also get a lot of electronic encoders now which are using a serial interface. But when we talk about an encoder using 5 or 24 volts, typically that would be an A quad B encoder, and we're using again either light or maybe an electromagnetic response, and we're inputting 2 different voltages, and we use the phase between those voltages to work out the rotational position. I'll come on to a few more industrial devices in the next few slides. High voltages and AC voltages are rarely used. We used to see a lot of circuits using 48-volt DC. 48-volt DC is at the limit of where you could get an electric shock, and also it's a bit higher than the 24-volt DC and a bit harder to handle. You need slightly bigger insulation, although the benefit is as the voltage goes up, then that means you can potentially reduce the size of the conductor because the current goes down, but you do need to increase the size of the insulation. 125-volt DC was also common. For the UK, for example, 48-volt DC was common in circuits like telecommunications, 125-volt DC common in railroad applications, but they're generally being phased out right now. One of the big problems with DC voltages, as they get higher, a DC voltage can easily overcome certain sorts of resistance, and then when it encounters a human, then that can cause an electric shock. And because the DC current's going in one direction, it effectively means that your hand or whatever that's touching the electricity is frozen because the DC is only going in one direction. So quite dangerous, but also difficult to handle. Manipulating those higher voltages, the semiconductor devices need to be a lot bigger, and construction was a lot harder. So lots of reasons why 48-volt DC and 125-volt DC are phased out. Now, we do occasionally see 110, 120-volt AC for outputs. When I talk about these voltages, by the way, there are nominal voltages, and they vary from country to country. So, for example, in Europe, the nominal mains voltage is 230 volts AC. That was standardized by the European Union many years ago. But what they did was, because of the different voltages in use in different countries, and this is the same with 110, 120 volt AC, what happens, you might find that there's a nominal 230 volts, for example, but the actual voltage range, it has a percentage, and it means that the actual voltage can be 240 volts AC. So we see that a lot in the UK. Everything is nominal 230, but if you were to measure it with a multimeter, you'd actually see 240 volts. So that's why we use this combined nomenclature of 110, 120, or 230, 240. So 110, 120 volt AC is sometimes used for outputs. The reason is that because you've got a higher voltage, you can have more power, or alternatively, you could potentially have a smaller conductor because you've got higher voltage and lower current, because they are directly related. And I'll come on to some calculations later, but generally higher voltage means lower current and vice versa. So higher voltage means that you could have lower current. Alternatively, you can have the same current and then you can get more power, because power is related to voltage and current as well. So having a higher voltage, that helps you have higher power, particularly for larger outputs. 230 volts, 240 volts, again, sometimes used. We see that in the UK and some parts of Europe. The problem with these voltages is they are higher volts and they can cause electric shocks. Generally, anything above 40 volts can be enough to overcome your skin resistance and cause an electric shock in humans. DC voltages are particularly dangerous because they effectively lock your muscles and you can't get away from the electric shock. At least with AC, because it's alternating, you can generally be released from that. Very high voltages, of course, very dangerous because they can cause serious burns and injury. If it goes across your heart, it can stop your heart. So there are very big issues in using high voltages. So coming back to the top line there, as we say, most industrial devices today use 24 volts DC. Now we talked about PLCs. Industrial PCs are slightly different. They do tend to use multiple voltages, but the voltages are normally split into the mains voltage, which is used for the power supply, and then internally we get voltage regulators which have much lower voltages inside. So typically for an industrial PC, 24 volt DC is common. Some industrial PCs use higher level mains voltages, but if you've already got 24 volt DC in your panel, it's more convenient to use 24 volt DC. That means that the electronics inside the IPC can be simpler and you don't have to get rid of as much heat. You don't need big transistors or switching power supplies. 24 volts is more convenient for most applications. Again, it's also safer. Inside the industrial PC, there can be multiple voltages. So 24 volts DC is often converted down to 12 volts. 12 volts is a common speed or power for fans, although industrial PCs today rarely use fans, depending on which your vendor is. 5 volts is often used for the main internal electronics because 5 volts is the voltage for TTL electronics. 3.3 volts is used for a lot of internal electronics, and 3.3 volts is what's used for CMOS type electronics. But these days, because the voltages and the distances within inside the CPUs are very, very small, we could be down to a few nanometers. High voltages could easily cross those small distances. So as we get smaller and smaller sizes inside the electronic components, the voltages are getting lower and lower. So we often see some CPUs which are running on just over a volt or so, but all of that is safely inside the industrial PC. And you don't generally need to worry about that. It's just the incoming power supply voltage that's of concern. And possibly if you are applying a fan, then you might need to worry about that as well. So coming back to PLCs, PLCs have inputs and outputs that are used to control input and output devices. So inputs are typically sensors coming from the plant. Outputs are devices we use to control the plant. So I/O devices include discrete or digital devices and analog devices. Discrete is either on or off, or 0 or 1, or 1 or 0, depending on what the logic is. It's a digital signal. So some people use the term discrete, some people use the term digital. They're interchangeable. Typically these are 24 volt devices and they use DC. 24 volt AC, you come across that occasionally in older systems. 48 volt DC I mentioned is common in telecoms. 125 volt DC used to be common in railroad and transportation type applications. 110, 120 volt AC is common, again because of the higher voltage gives you the more current, as we described earlier. 230 volt, 240 volt AC sometimes used in the UK, but mostly it's 24 volt DC. Now an analog signal, this is a variable signal, and we use this to represent some variable in the field which can vary from multiple values. So for example, we might be monitoring a pressure or a flow or a speed, and they could be variable depending on what it is we're monitoring. Typically we use 4 to 20 milliamps. 4 to 20 milliamps is the commonest analog value. The reason is that it gives us protection against a short circuit on the wire, because the minimum is 4 milliamps. If there was a short circuit or an open circuit, that would either go above 20 milliamps or below 4 milliamps. So we've got some built-in fault checking there. But the other benefit of 4 to 20 milliamps are easily handled by modern electronics. And also with a 4 to 20 milliamp signal, it's current based. So what you typically have is a twisted pair cable going to your device. And if you had any electromagnetic interference, it would affect both pairs equally. So 4 to 20 milliamps is relatively immune to noise, even without using any shielded cables. So 4 to 20 milliamp has become the industry standard for most analog values. So for example, if you're measuring speed, 4 milliamps might correspond to 0 speed. 20 milliamps, that might correspond to full speed, 100%, or whatever your rotational value is. Same with level. 4 milliamps might be empty or 0%. 20 milliamps would be 100%. Some people use slightly different variations of that in order to allow for alarm limits. It's also possible for some circuits to go below 4 milliamps and above 20 milliamps, in which case you could get an under range or over range signal. But typically the actual nominal value on the wire is 4 milliamps represents 0 and 20 milliamps represents full scale. Sometimes we see 0 to 20 milliamps. That's also possible, but then of course you have the issue that if there was an open circuit, it would be at 0 milliamps, which is also the zero signal. So how do you know if you've got an open circuit or if you've got an actual real zero signal? So for that reason 4 milliamps is preferred. We do also see voltage signals. We can see 0 to 10 volts. So again, 0 is 0 and 10 would be the maximum. The downside of this is that with 0 to 10 volts, first of all, because it's a voltage signal now, it's more prone to electromagnetic noise. So you have a challenge there. Another problem is that you're handling the voltages. It's a bit trickier than handling the current signals. You potentially need shielding. You potentially need more protection on the inputs and the outputs because you've got a voltage rather than a current. You can't just use a resistor. Also, with those voltages, because they're quite small, you get an issue with, for example, diodes. If a diode drops the voltage by 0.7 of a volt, then that's affecting your actual voltage reading. So voltages are used, but less commonly than current values. We can also see plus or minus 10 volts. That's if you want to go negative. For example, you might have a speed that can go from minus, say, 1000 RPM to plus 1000 RPM if you've got a reversing motor. So you might see plus or minus 10 volts to represent that speed. And we also see 1 to 5 volts. There's a direct relationship between 1 to 5 volts and 4 to 20 milliamps if you're using the correct resistor. So that's why we see 1 to 5 volts. But 1 to 5 volts has the problem that it can be affected by electromagnetic noise. So rarely seen. More often it would be like a 4 to 20 milliamp signal. Now, when we convert an analog signal, inside the PLC, it's represented as a value inside a register, and that register is a digital number, typically using 2's complement. So, for example, if we have 0, then it's simple, it's 0. If we wanted to represent a number of, say, 64, then we would have a binary representation where one of the bits is on within a binary number, and then that appropriate bit for 64 would be on. And then for other values, you'd have the appropriate bit pattern according to what the analog value is. So what this means is we have to convert from the analog value that's coming in, which is an infinitely scalable value in theory. We have to convert that into a discrete value, and we do that through either an analog to digital converter, if we're converting analog inputs into digital, or if we've got analog outputs, then we do that with a digital to analog converter. So resolution is the number of bits used for conversion. More is better, but the more resolution you have, generally the more expensive it gets. And you also have to offset this against the actual errors and tolerances within the system. For example, if you have a typical resistor, a resistor has a standard tolerance of 10%. You can get finely tuned resistances of down to 1%. Inside an analog to digital conversion signal, you might go down to a conversion of 0.1%. But what that means is, once you get to a certain resolution, your accuracy of your signal is offset by the actual accuracy of the conversion. So you end up having more bits, but you don't necessarily have a more accurate signal because the electronics outside affect your overall accuracy. So more is better, but it does cost more, and there is an eventual point where there's no point having more resolution because you just end up just having noise in the signal and you're not necessarily reading with more accuracy. Typically what we see is 12 bits is common, and that would give you a value of 0 to 4095. So 0 for 0 and 4095 for your 100% signal. Or you might go minus 2000 to plus 2000 approximately if you had plus and minus values. Commonly what we see today is 16-bit resolution. There's not much point in going more than 16-bit again because of that 0.1 resolution of the physical hardware. There's not much point in having 16 bits, and even with 16 bits you've still got some extra resolution there that isn't used. But many common analog to digital and digital to analog converters are now 16 bits. So that gives you a number of either 0 to 65,000 approximately, or plus or minus 32,000. and you can see the exact numbers on there. The reason we've got those funny numbers like 4095, 65535, that's the relationship between the digital representation using 12 or 16 bits. And I'm not going into any more detail on that. That's outside the scope of this particular session. Now, some modules allow scaling into engineering units and floating point units. Depending on the technology inside your PLC, rather than have a number of 0 corresponding to 0 and 65,535 corresponding to 100%, you might scale directly into engineering units. So if you were looking at a tank level, then you could have a floating point value where 0 is 0 and 100% is 100. And then you can represent all the numbers you need between 0 and 100, depending on what the resolution of your floating point value is. And that would be dependent on what your PLC technology lets you do. So of course that makes it a lot easier, because rather than needing to think about, well, what's 50%? So 50% with a 12-bit system would be 2048. You can just say 50% is 50, and that can make it much easier to read compared to the binary representation. So a lot of modern PLCs do allow that floating point. The downside is with floating point, sometimes the hardware can be a bit more expensive. You need to buy a bigger, more expensive PLC. And with some PLCs as well, it can affect performance. Handling floating point values takes longer than handling digital values. But with a modern PLC, speed is rarely an issue. So it's more convenient for the user generally to work in the floating point value. So typical industrial I/O devices. Discrete inputs includes things like push buttons, limit switches, and proximity sensors. So a push button is used by an operator. They would push the button to start a machine or stop a machine or reset a machine or change its state. Limit switches and proximity switches, they can be used to sense when something is present or at a particular location. So for example, in a pneumatic solenoid, we typically have a limit switch at each end, so we know when the solenoid is at that limit of travel. So there would be a extended limit switch and a retracted limit switch. A proximity sensor, that could be used to sense when a part is present. So for example, if you have a box on a conveyor, you might use a proximity sensor to detect when there is a box going past that point in the conveyor. Discrete outputs, that includes lamps or indicators, which are used for notifying the operator of something that's going on. So you could have a lamp to indicate what the status of the machine is or to indicate faults. Solenoid valves, I mentioned, these are pneumatic valves which can be used to transmit a physical output, to push a slide in one direction or another. That can also be process valves as well. So a solenoid might be used to control a process valve and open or close that valve to allow or prevent flow of materials. We can have relays, which can be used to switch lower voltages and currents to higher voltages and currents. And then contactors, as I mentioned, very similar to relays, but they switch even higher voltages and currents, typically to control, for example, a motor. So you'd use a contactor to turn the motor on or turn it off. You might also use a VFD today to control a motor. It depends on the size of the motor and what other considerations there would be for controlling your application. But typical I/O devices, push buttons, limit switches, proximity sensors, lamps, solenoid valves, relays, contactors. That's typically what we see in a common machine. Analog inputs include potentiometers, often used by an operator to control the set point of a machine. So a potentiometer is actually a variable resistor, and by moving the control knob, you can control the resistance to the device, and then that can control the current into the PLC. So we could read that with an analog input to work out what the potentiometer position is. On the machine itself or the process, we might see flow meters, pressure meters, level meters, temperature meters. They typically come from some sort of transmitter device, which gives us an analog input, which again could be read back into the PLC. And then we also see feedback from VFDs. There might be a tacho on the end of the motor shaft, and that gives us a voltage based on the speed of the VFD. But more typically with VFDs, the VFD communication to the PLC would now be entirely electronic, using a protocol of some sort over some sort of network, typically Ethernet, possibly serial. So VFD feedback can be done through an analog input, but more commonly it's done by electronic means using some protocol. Analog outputs, yeah, that could be a gauge or indicator to tell the operator what's going on. We might be controlling the position of a process valve to control the flow of material. There could be control signals to VFDs. I do see this quite commonly. You know, for simple VFD circuits, we'd have a plus or minus 10 volt speed reference to tell the VFD how fast to move. But again, more commonly with VFDs, they're migrating to electronic signals. So typical devices, again, you know, transmitters to tell us the status of the plant, and then various outputs to control the control aspects of the plant. Process valves can cover a multitude of parameters. We might be controlling the flow into a tank. We might be having a process valve that controls the flow of steam, which can control temperature. We might have a proportional valve which can control pressure. So process valves can cover multiple physical aspects of control, even though they're the same category of device. There are more categories of industrial I/O devices. These typically need more complex interfaces with more specialist handling of the incoming or outgoing signal. So for example, we have temperature inputs, thermocouples or RTDs or resistance temperature detectors. We might be reading voltage or current from a motor or an electrical grid. Voltage might be straightforward, but often we're dealing with a mains voltage. So that might mean some sort of transformer to convert to a lower voltage we can read. Current, you know, again, we often need some sort of transformer there to read that voltage or to read that current and turn it into something we can read, again, like a voltage. Stepper motors. Stepper motors are pretty straightforward in terms of the output requirements. It's normally a discrete signal that's on or off. But what you need with a stepper motor is to control maybe multiple outputs, and they can be quite high current outputs as well. So also they can switch very quickly. So it might not be enough to use a relay or contactor. You might need some bigger sort of transistor to actually control the stepper motor value in order to actually make it move in the direction and at the speed you want. Encoder I mentioned briefly, you know, A quad B is common, where you have two signals with a phase relationship between them, typically two 24 volt signals, and there's an A signal and a B signal. And what happens is you read the two inputs. If the A is leading the B, it means you're moving in one direction. If the B is leading the A, you're moving in the opposite direction. And then based on the speed of those signals, that they'd typically be two square waves, yeah, that's how you can calculate the speed of your motor or device. More commonly, we see serial interfaces now for encoders, such as SSI and others. And we can also get general serial devices. These need specific serial interfaces to handle the different electronics. Typical serial interfaces are RS-232, RS-422 and RS-485. And then there may be other types as well, but yeah, these are the ones that you'll commonly come across from a PLC point of view. Now, we talk about I/O being inputs and outputs, quite straightforward, but there may be a requirement for isolation. In a PLC, it may be some distance away from where the actual devices are, and because of that distance, you can get spikes on the wires that connect the PLC to the actual I/O itself. So sensitive PLC electronics, they may need protection, and those voltage spikes, you know, from EMC, they can be very large, and also there's even a potential for short circuits onto an I/O device. For example, if you've got a wire which is carrying a high voltage and that gets eroded over a long time, you know, the insulation can break down, or maybe there's some sort of physical damage. That high voltage from those inputs on the one wire could actually be fed into the PLC through direct electrical connection. It's also possible for people to make mistakes as well. I've seen that before, where, you know, normally this happens at the site acceptance testing, where you first connected everything up and you start powering it on. You might find for some reason you've connected a high voltage input to a low voltage circuit by mistake. That can happen as well. So it is a requirement to protect these sensitive PLC electronics from larger voltages and these big spikes. Isolation from the PLC I/O to the backplane is common. This would protect the PLC electronics from a spike on an I/O module. And the reason that's common is, you know, that's often required, and I believe it's part of the IEC 61131 Part 2 specification, which mentions various isolation from I/O to the backplane. Typically there you want at least 500 volts of isolation, but some modules offer 1000 or even 1500 volts. And also you have to consider the time of the error how long the actual voltage is going to be present. Ideally that would be a continuous protection, but some devices only protect for up to a minute or so before the insulation breaks down. Now this costs more, but you can also have isolation from PLC I/O to other I/O on the same module. So group to group or point to point isolation, this depends on the individual I/O module. Module to module is very common because typically you've already got module to backplane, and then if you've got a backplane, module to module communications via the backplane, so that's often provided as standard. You might have group to group isolation on the same module. For example, you might have a 32-point module in 4 groups of 8, and there would be isolation between those groups. And then the most common one, or the rather advanced one, is point-to-point isolation, where an individual point is isolated from all other individual points. That's not common because you need an isolating circuit on every single input or output, and that means more electronics and more cost, and also more terminals because you need to have separate terminations, so it can make the modules bigger as well. So there's both an impact on size, an impact on cost, possibly an impact on complexity as well. But module to module, group to group, yeah, we commonly see that on most PLC type devices. And then point to point, that may or may not be there, depending on what's needed for your application, but you do often have to pay extra for that one. So let's consider a discrete input device, typically an electromagnetic device. So what happens there is you have mechanical movement, and that engages or disengages an electrical contact. So for example, a push button. Push button is held out by a spring. When the push button is held out, you have 2 contacts which are apart from each other. When you push against the spring, then that pushes the contacts together, and then that engages the current flow. When you release, the spring pushes the button out and the button retracts and the electronic contacts come apart. Similar with a limit switch, you'll often have a spring, and then as something mechanical comes past the limit switch, it pushes against the spring, closes the 2 contacts, and when the contacts are closed, you get electrical current flow. So very straightforward. You can see some wiring diagrams over on the bottom right here. A simple input device is just indicated by a break in the wire there, and you can see there's a small line in the middle, and that's your input device. When it's open, of course, there's no power because there's a physical gap. When the input is closed, then you get power through the input device, and that typically comes from a positive voltage, your 24-volt supply, into the input to the PLC. So logic is quite straightforward. Closed is passing power, which is measured as 1. So typically what you'll see in the PLC is you'll see a discrete or digital bit. 1 means on or closed or true. And if it's open, then there's no power flow, no current flow. So that's typically represented as 0 or off or false. Now some devices have their own electronics, so you would have an advanced input device. It would have a positive voltage and a 0 volts, which would power the device itself, and then the output from the device would again be the input to the PLC. So I've shown that on the bottom right there. Okay, but generally straightforward devices, an electrical contact, and the contact is open under normal circumstances, and it closes when something happens on the plant to make it close. It's possible to have it the other way around as well. You can also have it where open is on and closed is off. So that would be like a reverse acting device. The electrical circuit for that is slightly different, but effectively we're just reversing the logic. That's common in things, for example, like emergency stops, where the safe state is open, but when the emergency stop is tripped, that means you've got a 1 for the emergency stop is effectively triggered, but the actual circuit itself is open. So open in an emergency stop is often the value of 1 inside the PLC. But that depends. It depends on whether you're using the main input circuits for an emergency stop. Sometimes there might be an auxiliary circuit you're reading, which could be the opposite in terms of logic. So what you need to do when you're designing systems is you need to look at what the relationship between the open and closed status is versus the logic status. And it doesn't apply too much when you're actually doing the wiring, but it certainly applies when you start doing the PLC programming. So inside the PLC, we have potentially multiple electronic components in order to actually handle the inputs. So typically there would be 24 volts, which is wired to a PLC input module terminal, and that would come through your input device. And then that would go into typically an optical coupler, and the optical coupler is what sends a signal to the PLC electronics, and then that gets read into the PLC data table to tell you whether that device is on or off. Additional components could include a resistor to limit the overall current and protect that optical coupler. There might be a capacitor as well. The capacitor can be used to eliminate AC. There might be a voltage limiter via a Zener diode to prevent, again, damage to the optical coupler. And there might be a reverse voltage protection diode to eliminate the back EMF when you have that collapse of the output from the, for example, a solenoid or a relay. Rare on inputs, but possible. So you wouldn't always see these, but typically this is how an input works. And it's very common to have the isolating device or optical coupler because you want to protect the PLC backplane from whatever the input electronics are. Now, once inside the PLC backplane, that signal from the optical coupler, that would be fed to a buffer integrated circuit. That would then provide the signal to the backplane, and eventually via whatever electronics are required, that would end up inside the PLC's data table. And the relationship of the electronics there, that would depend on, is it local or remote I/O? What sort of communications have you got across the backplane? Is it serial or parallel? Are you using remote I/O on a particular network, such as Profinet or Modbus? So there's a lot of potential issues and complications in there, but they're really beyond the scope of this discussion. So typically, as we see, the input comes in via your input device, such as your limit switch or your push button. It goes into the plus V input on the input module. There's a variety of potential protection devices, which may or may not exist. It will depend on the module. Obviously, the more protection you have, the more it costs in the module. So that puts up the cost of the electronics. And then you have that typically optical coupler that gives you the isolation between the input and the backplane. Now, it is possible to have very few or no electronics in there and just have the optical coupler, and it could be that the protection devices, the resistor, the capacitor, the voltage limiter, that reverse protection, they may all be external on field terminals that are used to wire the device to the actual field. Because we're talking about long wires, you might have a PLC in a cabinet, the actual machine might be several meters away, so there is some wiring there. It's very common to have field terminals, so those protection circuits could be applied at the field terminals rather than at the PLC themselves. So your input circuit will vary, and you'd have to consult the PLC vendor's documentation to understand exactly what that input circuit looks like. And then depending on your application, you may or may not need to add the additional protection. And also, what's your tolerance to risk? If you're just preparing or protecting against a short circuit, what's the likelihood of that short circuit? You may decide that if the input module is very low cost, it's cheaper to sacrifice an input module now and then rather than have a lot of expensive protection circuitry. So I mentioned the input circuit protection. So in more detail, we have the resistor. The resistor can give you protection against current, but it can also provide a minimum load. Some electronic output devices, particularly some limit switches and proximity switches, they need a minimum load to actually drive the electronics. Without that minimum load, then you effectively get nothing out of the device. And the reason you need that resistor is you do have resistance through the optical coupler, but the optical coupler is normally a very light load. It might be talking in terms of microamps or fractions of a milliamp, and that's not enough to trigger the device. So the resistor might be required to drive a bigger load on the device and make sure that the device can actually operate. The capacitor, that's generally used to filter AC voltages and eliminate AC from the circuit. Probably not required, but again, depending on what your input is, you may want to filter those voltages, hence the capacitors required. To prevent overvoltage from damaging the optical coupler, you use a Zener diode. Again, not very common to do this. Normally you would just take the risk and sacrifice an input module if there was a high voltage, which is rare. But if you wanted a lot of protection because you'd had a lot of issues, or maybe you were really concerned about a high price of input module, then a Zener diode might be fitted. The reverse voltage protection diode, the normal use for that is actually to protect against input miswiring. Now, with many optical couplers on modern PLCs, they can handle voltage in both directions. So what you'll see is on an input module, it can handle both positive and negative logic. So it doesn't matter what the voltage wiring is, but you might want to protect against miswiring, and you might want to make sure that if it's wired the wrong way, you don't want the circuit to operate, or maybe the optical coupler only operates in one direction itself. So that diode could be used as an additional form of protection. And as I mentioned, with the back EMF, it can also protect against those high voltages from certain devices. We wouldn't normally see those high voltages on an input circuit. They're normally related to output circuits. But again, it just gives you more protection by having these multiple devices here. The optical coupler, that's normally standard inside the PLC. Your PLC vendor might not mention what sort of device that is, but typically there's always some sort of isolating device there. Normally it's an optical coupler because they are these days the lowest cost, and they operate at high speed, and they give you good levels of isolation. And as I say, for the IEC 61131 Part 2 standard, you have isolation between the PLC electronics and the field terminals is very common. So just a bit more detail there on what the discrete input circuit protection might look like and why you need it. The key one I found is resistor to provide the minimum load. That's very common. The others, much less so. They're much less required. And even on the resistor, that's going to depend on what your device is. Typically that's only required for certain sorts of proximity switch and electronic type input where you do need that minimum load. To calculate what the minimum load would be, we've got some calculations later to talk about resistance, but normally what you would do is you'd look at the data sheet for your device, and that would tell you what the minimum load is, and then based on that you could compare that with the PLC load of the optical coupler, and then you could add additional resistance if required. So resistors common for certain loads. The other ones I would say not normally required, and the isolating device is pretty much always there because that's what the PLC input is using. So I've mentioned positive logic and NPN input wiring. This is the most common type of wiring, and in fact it's so common now it's normally taken for granted that what you will have is a positive or NPN type input circuit. This is mandated in Europe by the Machinery Directive. The reason is this avoids any confusion over how the logic operates, but there's still a safety potential, of course, when we consider safety like emergency stops. But generally, this is the easiest to understand. It's quite simple. When your input device is on, your logic is on, and you have a true input. And when the input is off, there's no voltage or current, and that means you've got a signal of 0 and false. And the reason for doing this is it's fail safe. If anything happens to the input circuit, typically that's an open circuit, then the input in the data table goes off, and it means that your input is off, your logic stops operating because the input is no there, and it's generally safe and easy to understand. Do be careful though, however, because this logic, it might be fail safe for an open circuit, but you could still get a short circuit. So this is not intended for safety purposes, although sometimes if there is a safety system it will still use this positive logic. But positive logic by itself doesn't guarantee safety, but it does simplify the wiring and the understanding of the system. The opposite, of course, is a negative logic, and that's where the voltages and the states are reversed. So with positive logic, quite straightforward. You have your input coming in through your input device into the input module. The input module electronics handle that and turn that into a 0 or 1 inside the PLC data table. And to complete the circuit, you do need a return, so you always have to have a way for that current to get back from the original supply back into the power supply where it came on from. So normally at some stage the input module would be connected to 0 volts. So there's a very simple representation on the top right of what your circuit diagram would look like. It may be a bit more complicated because the 0 volt might be shared across multiple modules, and that 0 volts might even come out on a separate terminal on the PLC, depending on what type of PLC you've got and how the internal connections work. So some PLCs give you 2 terminals for your input device, the positive input and the 0 volt return. Some just give you the input and the 0 volt return is made elsewhere. So what we can see here is we've got the positive voltage going through the input device, and effectively the current or the voltage from the input device is sourced into the input module. So the input module is effectively sinking the current from that device. So you'll hear terminology about sink and source, but from what I've just said, you'll already see that's confusing. You know, we're sourcing current through the input device, but sinking it into the input module. So is it sink or source? So I prefer to use the terms positive logic, and positive logic means we're representing a circuit like this. And more importantly, it means a voltage of on and current flow on equals 1, and the voltage off or no current flow means 0. And in logic terms, 1 is true, 0 is false. Again, that's not always taken for granted either. You'd have to look at the actual PLC representation. But in any modern PLC that's controlled under the machinery directive, which is mandatory for Europe, on is always true and off is always false. Okay, as you've seen from the previous slide, we do get the possibility for an optical device which can work in both directions. What you will find is many modern discrete input modules can be wired for positive or negative just by reversing the input signals. So in that case, we're not really distinguishing positive or negative in terms of the module hardware, but we are distinguishing in terms of the wiring and the overall operation of the device. So here's the opposite wiring, negative or PNP. So the arrangement now is in the reverse. We've got a positive voltage that goes into the input module. Then we've got an input terminal that goes through the input device down to 0 volts. This is not really allowed by the machinery directive. You do sometimes see this used for interfacing between systems where you're using discrete logic to interface. So you'll get a positive output going to a negative input or vice versa, but again, very complicated and confusing because it's hard to know which way around the voltage is. And here's the real problem: negative logic, when the voltage is on, it means you've got a value of 0 in the PLC or a false input. When the voltage is off, you've got a value of 1 or a true input. And if the input fails because of an open circuit, that would give you a data table input going on, which might be the opposite of what you want. So it's certainly not fail-safe. Again, you've got confusion about sinking or sourcing. This can be problematic from a control and an understanding point of view. So generally we try and avoid it. As before, most modern discrete input modules can be wired for positive or negative just by reversing the polarity of the wiring. But from the machinery directive in Europe, which is a European Union regulation, and also for simple understanding, it's much preferred just to use the positive wiring rather than this negative type wiring. So ignoring the positive and negative connection, the single wire discrete input connection typically looks like this circuit diagram here. We have a single terminal for the input on the input module, which comes from the input device, which itself is provided from positive voltage. Sometimes the input voltage on the input device that might be derived from its own internal electronics. If it's a passive device just involving a simple contact, then you will need that positive voltage into the input device. That could either be sourced externally from the PLC panel, or you might have terminal rails inside the PLC panel that provide that positive voltage. So that's normally outside of the PLC scope itself. Some PLC modules do have the 2 wires or even 3 wires to provide that positive voltage, but that depends on the PLC module. Usually you just find on the input module there's just 1 or 2 terminals. The input module, of course, it also needs that 0 connection as I've described, because you have to be able to pass the current back to the source somehow. So on the input module you'll either see an input and a 0 volt, or maybe just an input and the 0 volt is elsewhere. But the overall wiring looks like this. So again, think of the current flow. You've got the positive voltage coming from the power supply somewhere, possibly via terminals, going through the input device, passing current into the input terminal on the input module, and then the 0 volt to return back to the 0 volt on the power supply. So this is what the 2-wire discrete input connection might look like. You'd have 2 terminals for the input device on the input module, a plus volt supply, which is the 24 volts going out to the input, and then a return, which is the actual input signal itself. So in this case, the input module is handling the plus volt connection, and this makes for simpler wiring. It eliminates the requirement for an external terminal rail. That reduces installation costs and panel space. The input module has both the plus volt and 0 volt connections. Of course, you still need those plus volts and 0 volts to actually get the power from the power supply in the first place. But what this can do is considerably simplify the actual external wiring to the input device. You might still need a terminal if you wanted any of those protection mechanisms we mentioned earlier, because otherwise they might not exist. Although in practice you probably don't need those if you just had simple contact inputs, and you don't even need that resistor unless of course those were going to be some sort of proximity type device which maybe meets the minimal input resistance itself. But this can certainly simplify your I/O wiring, but it also means that the PLC vendor has to do more work because they have to provide those terminals. So that might mean, depending on the module, maybe you get fewer channels because you've got to now dedicate an input and an output to the device. So now you need 2 terminals instead of just 1. So for example, where a normal module you might have room for 32 or 16 channels, now maybe you've only got room for 16 or 8. But of course that's offset against the simplicity of the wiring connections by the user. So we do see this in some systems. It's maybe worth looking, depending what your priorities are, to see, would you rather install those extra input terminals on the terminal rail and you have control over what the terminal rail and the connections look like, or would you like to simplify this and just rely on what the vendor offers? And with modern electronics, this is quite feasible to do, and not that particularly expensive in terms of the I/O wiring or even the electronics to handle this. Let's take a look at discrete output devices. As we saw before, these are typically an electromechanical device, such as a relay or a contactor, maybe a lamp or some other sort of indicator. But the idea is electrical power flows through a coil and that causes mechanical movement. So we've got concepts of like a pneumatic cylinder, maybe a valve, a relay coil or a contactor. And normally it's quite straightforward. The mechanical device operates when current passes to the device and then returns to 0 volts, as you can see on the circuit diagram at the bottom here. So you've got the output from the PLC, the output device, here represented by a circle, and then 0 volts. This is positive logic, of course. On means energized, which is 1 or true, and off is de-energized, which is 0 or off or false. Here's what the discrete output circuit looks like from the PLC point of view. You have your transistor, which is part of an optical coupler device. So in this case, you can see the transistor circuit in the right there. You've got the circle, you've got the emitter and the collector, but the base now is actually coming from a electronic device which registers light inside the device. So you've got the 2 small arrows there which represent a light input, and then you've got your big output terminal, and then of course you still need a 0 volt or return, and of course you need the plus volt connection. So the 24 volt DC device is wired to a PLC output module terminal. Any output module may also need additional circuits. For example, depending on what you're driving, for most solenoids you do need some sort of back EMF protection via a diode. You may also need additional protection circuits as well. For AC circuits we need additional protection. Maybe you need a resistor snubber network comprised of both a resistor and a capacitor to eliminate noise. In the PLC is protected because you've got that isolating device or optical coupler, so the backplane is normally always protected from the output terminal. So if any external protection is needed, it's normally around protecting the optical coupler itself. Now the output signal inside the PLC, there's again a buffer integrated circuit that comes from the PLC's data table, and then that's used to actually drive the optical coupler value. And then behind that there may be more electronics. Again, what's on the backplane? Is it serial or parallel technology? Are you using remote I/O? Is there something going on there with a remote I/O network on Profinet or Ethernet or serial networks and so on? So there might be a lot more electronics behind that, but that's outside the scope of this discussion. So with protection, this is what the final circuit might look like. We've got protection here on the output terminal. The first protection is a fuse to limit the current. The reason is that an output terminal, unlike an input terminal where the current is often quite low, you normally have a high resistance on the input. So even at 24 volts, the current is very low. But in this case on the output, because of the way the optical coupler works, that can supply the full current to the output device for whatever the optical device can handle. If there was a short circuit on the output, then potentially you could get several amps going through that optical coupler, and that's quite likely to damage that optical coupler probably permanently, so the output no longer works anymore. So one possibility is a fuse. Some devices do have their own protection built in. You'll see electronic short circuit protection or ELCP or various different terminologies there. But the idea of that is there's effectively an electronic fuse inside the module. But again, that costs more money because you've now got more electronics in the module. So very common to see a fuse on the output. If it's a DC device, you'd get that diode. That's your diode that gives you that protection against the back EMF caused by inductive loads. That's also known as a freewheel diode because of the way the voltage freewheels around the circuit when it reverses. And also you could get a resistor. A resistor provides a minimum load for the output. The reason for that is that on the optical coupler side, the older devices at least often had a minimum current. And if you were trying to drive a very low current output device, the output device would not draw enough current through the optical coupler to actually enable it to turn on, just because of the nature of the electronics and the semiconductors and everything else. So for some devices, it's sometimes required that you do have that additional resistor to increase the load and make sure the output will actually energize. Less common today, but still possible. I haven't shown all the fusing here as well. We've got a fuse on the output. That could be a fuse or a miniature circuit breaker. On the output side, there's often additional circuit breakers that come above the plus V at the top there. But again, that's really beyond the scope of this discussion. So various protection devices there, really just about limiting the back EMFs, possibly limiting the overall current, and also maybe a resistor to actually make sure that there's enough current on the output to make sure that it can energize properly. So just a bit more on overload protection. Again, some of this is beyond the scope of this discussion, but I'll mention it briefly here. Typically it's a fuse. So a fuse is a piece of metal that can carry so much current, and when the current exceeds the fuse capability, the metal melts and then goes open circuit. So they can be quite slow, depending how long it takes the metal to melt, and they can be quite variable in terms of the actual current, because it can be difficult to make a fine enough piece of metal that actually operates at that particular voltage or current. Another problem with fuses is they can also oxidize over time. So a fuse that's maybe rated at 2 amps when it's new, with oxidation, it may only be rated at 1.5 amps after a few years, and that could cause it to blow early. So fuses can be unreliable. So these days we often use miniature circuit breakers, or MCBs, also known as maybe molded case circuit breakers, or MCCBs. So these are small electronic devices. They're still sort of mechanical in effect, really. The way these work is they've still got a piece of metal inside. The metal heats up, but then the metal triggers a spring, and then that operates the miniature circuit breaker. Because we're not relying on a high current that actually burns through a piece of metal, the thermo characteristics of the spring can be more finely tuned, and also because you're not breaking anything and there's no oxidation, because you can use different metal types, they can be more reliable over a longer time. Ultimately though, an MCB can still break, and they are more complicated than a fuse, and they are more expensive. So you would have to choose either a fuse or an MCB or MCCB based on your requirements and your preferences and your experience and what reliability they are, and of course what the costs are. Now, it is common to have multiple current overload protection devices. As I mentioned, there would be a master fuse or MCB which protects and isolates the entire system. That's often quite a big fuse though, because it's controlling power to the entire control panel and maybe all the outputs going out of the control panel. So that might not trigger if there's an individual overload on the particular circuit. So what we also often do is have individual power supply fuses and MCBs which protect and isolate each power supply. It's common in a control cabinet to have multiple power supplies, maybe for redundancy, but also, say you might need 40 amps of power. Rather than having one big 40 amp power supply, you might have multiple 10 amp power supplies. Just makes it a bit easier to wire, and maybe that 4 power supplies is cheaper or easier to source from one big power supply. And it also means you've got a bit more protection there. If one of those power supplies was to fail, you'd still have the other power supplies, although depends which power supply failed first. So there might be multiple power supplies, each with their own fusing. You might then have additional branch fusing to protect each I/O module or each I/O drop. So that would give you additional protection. And then it's sometimes, but not always, you might go to the extent of having that individual fuse to protect each I/O point. That's more expensive, but that can aid fault finding. If you've got an individual output where the fuse has blown or the MCB is tripped, it's easy to find out what's gone wrong there, because that takes you straight to the fault rather than maybe only bringing it down to an individual I/O module or section of I/O. But of course it costs more to do that. So positive or NPN output wiring, this is by far the commonest. We have our NPN transistor as part of the output coupler. So positive voltage goes into the output coupler. It's triggered by the optical coupling mechanism from the PLC. So positive logic, again, 1 is true and the output turns on, 0 is false and the output is off. This is sort of fail-safe because in the case of most common output issues, the output goes off. But again, it's not intended for safety purposes. It's possible that that output coupler could go short circuit, and there are other potential modes where maybe something in the PLC backplane is driving the output on even when you want it to be off. So if you need safety systems, safety systems are separate from just relying on the fail safety of a standard device. But in principle, this is fail safe, and again, easy to understand. When the output is on, the output device is operating or energized. So for example, the relay contact would close or the solenoid would operate. Nice and easy to understand. And again, you've got that degree of fail safety there. Your output device is wired from the output module terminal to 0 volts. You do need a return path for the current. And this is where sync and source makes a bit more sense. In this case, the output module is sourcing current to the device. But equally, some people talk about the output device syncing current from the output module. So still a bit confusing to talk about sync or source. But normally, if we're talking about sourcing, we mean the module sources current to the device. But better to use that positive logic. Again, this is most common. The machinery directive it advises against or prohibits negative logic. The only option for negative logic is for very old legacy systems or maybe for interfacing between two devices. So contrast that with negative or PNP output wiring. This time the output device is connected via the positive rail to the output terminal, and then the optical coupler sources the current through the output terminal down to 0 volts. Possible failures here, of course you've still got the possibility that the optical coupler could go short circuit, but if there was an issue with the output wiring on the negative side, that could lead to the output device energizing because it's connected to positive voltages. Again, compare that with the previous one where the output device isn't connected to any positive voltage except via the optical coupler. So potentially the risk here is a bit higher. Again, it's not allowed by the machinery directive other than for interfacing between systems. And the biggest challenge is negative logic. Your developer of your code has to say, okay, well, when I want this to come on, I need to turn it off. And when I want it to go off, I've got to turn it on. So very confusing from a logic point of view. And also from a maintenance point of view, a maintenance engineer looking at this application to work out, is it on, is it off, should it be on, should it be off? Very confusing, so best avoided. Again, you've got this sync and source technology or terminology. You're syncing current from the device into the output terminal. So that normally makes sense. But again, some people might think about the output device sourcing current to the output terminal. So again, still possibilities for confusion there. So we normally use this negative terminology, negative logic, but again, best avoided, rarely used, really only seen in legacy systems, and very rarely where you're interfacing systems where you have a positive output going to a negative input and vice versa. But even then, that's not very common these days. So this is typically what we see, a single wire discrete output connection. The output module is wired to +4 volts. That goes through the internal device inside the output module. So refer back to previous slides for what we can do there. You've then got the output terminal, which goes to the output device. And of course you need a current return for the 0 volts, typically via a terminal rail. So quite straightforward, and that's most commonly what we see, and that's a single wire type of discrete connection. So you'd need a terminal rail to handle all of your 0 volts, and then you might need additional terminals to handle the interposing outputs, but relatively straightforward. This is what a 2-wire discrete output connection might look like. you've now got two terminals for the output device on the output module itself. So there's an output signal which comes from the output module and the 0-volt return, both handled by the module. So this can simplify your wiring to the output device because you don't need that intervening terminal rail. Again, it might cost slightly more, and it means that you've also got to handle the additional terminals on the output module, so it might reduce the I/O module density, but it can significantly reduce your costs in terms of the output wiring. So of course, you still need the output module positive and 0-volt connections, so they're still required. But again, can considerably simplify your wiring, reduce installation costs, also reduces panel space, which can be quite significant. But again, you'd also have to check to see, have you got the required output device? Have you got, for example, that freewheel or back EMF diode? Have you got any resistance that might be required in order to be able to operate the device? So it does need some investigation to make sure this will work, but this is becoming increasingly common to reduce the amount of wiring there is and to reduce the overall system costs. Analog input devices have a variable value, hence that's why they're known as analog, and these may be electronic or electromechanical devices. In electronic devices, the device's electronics themselves create the analog value, so that could be, for example, temperature, flow, pressure, level, speed, distance, and so on via a transmitter. And with these devices, because they're electronic, they generally need some sort of their own power supply. With an electromechanical device, mechanical movement increases or decreases electrical resistance to vary current or voltage, typically by moving a mechanical pickup across a variable resistance of some sort of material, maybe carbon or maybe a wire wound type resistor, and that device is called a potentiometer. So in this case, it doesn't need a supply, but it might do depending on how the input's arranged and depending what the range of a potentiometer is and some other factors as well based on the input resistances. So yeah, potentiometers aren't used very often because they can be a bit complicated. Also, the way the current can flow through the potentiometer can cause increased wear if a potentiometer is normally at one particular point, and also it can cause increased current flow through a certain part of the potentiometer, which can wear that potentiometer out. So maybe if you're like me, in the olden days we used to have an amplifier going to a record player, and it was quite common for that potentiometer to get quite sticky at times in terms of the actual mechanical performance, but then that stickiness was caused by wear and tear on the internal potentiometer, and that could also lead to noise and crackles as you change the volume. And that was because the potentiometer was this electromechanical device that was wearing out because it was used at a particular location all the time, and maybe that was heating up. You can also get grease or other contaminants on the potentiometer. So a lot of the time these days we see more electronic devices which are more reliable and also more linear as well. Linear means when you go from 0 to 100%, it stays the same all the way, whereas with a potentiometer you might get jumps where half it works less than 50%, but the other half might be more than 50% and so on. So you get a reduced amount of linearity, which makes those potentiometers quite unreliable and difficult to manage. Temperature input devices are different. You can have a thermocouple. A thermocouple uses two different types of metal joined at a junction, and what happens with that junction is, because of the different types of metal and the interaction between them at a physical layer, that creates a small voltage, and that voltage varies depending upon the temperature. It's a very small voltage, but what a PLC thermocouple input can do is read that voltage and then calculate the temperature. Now you need multiple different types. There are multiple different types. They have different characteristics. You may need a reference temperature to operate as well, often known as either a fixed offset or a cold junction compensation, or CJC. Another problem is the electronics. They have to deal with that small voltage, but they also have to deal with non-linearity as well, because that voltage can vary according to whereabouts in the temperature range you are. And those multiple types, there are lots of different two-wire types which have different characteristics, different voltages, and they cover different voltage ranges. So handling a thermocouple is quite complicated, but thermocouples have been around for a long time, and we can now do that quite straightforwardly with modern electronic input devices. Now RTDs, or resistance temperature detectors, these are slightly different. These use a single metal that changes resistance depending on temperature rather than two different metals creating a voltage. So it's resistance based. They tend to be more linear, they tend to be more accurate and have less drift than thermocouples, but they are more expensive and they don't offer such wide temperature ranges because the metal itself has limits in terms of its physical properties. But again, these days, if you have the required input and you know what your operating parameters are, it's quite easy these days to use a module that can read a thermocouple or read a resistance temperature detector. They can handle the resistances and the voltages, they can perform the linearization, and they can give you an output in terms of an analog value into the PLC. Again, depending on the PLC, that could either be a 12 or 16-bit, depending on the resolution. And also, of course, you could have a floating point value, which gives you a direct temperature reading in Fahrenheit or centigrade. So quite straightforward. It's just a matter of deciding, do you need temperature inputs? If you do, are you going to use thermocouple or RTDs? And then choosing the appropriate module and implementing the correct wiring. As I say, temperature input using a thermocouple, the complication there is that you do need that reference temperature. Typically that's a fixed offset, which is easiest. But if you have some sort of cold junction compensation, then that's another thermocouple into the device, which is used like a compensation value. And that can be internal, or sometimes for the best accuracy, it would be external. So again, there's this trade-off of cost versus complexity and accuracy, and also the temperature ranges and the simplicity of wiring and lots of other factors for those. So an analog input circuit is usually straightforward. We have the voltage or current device is wired directly to the PLC input module terminal on the analog input signal. That goes into an analog to digital converter, which may or may not be optically isolated, although usually it is. And then that goes to the PLC backplane. And then, of course, you've got your return signal, which must pass the current or whatever flow back into the power supply. Now, because analog to digital converters are quite expensive pieces of technology, they're an integrated circuit, which is electronics, depending on the resolution and depending on how the input works, it is common that some analog input modules multiplex one analog to digital converter between multiple inputs. So you also need to look at, are you going to get the response time you want? Because that multiplexing takes time. And that can also affect settling times. It can affect the costs, certainly. Also, you've got that issue of resolution and so on. But generally, that's a module internal value. And ultimately, what happens is you get a multi-channel module that takes in multiple analog signals and gives you multiple values inside the PLC data table. So you may have to look at the PLC vendor specifications to work out exactly what you're getting, but the ultimate result is the same. You just have to check that the speed and the accuracy and everything else matches your requirements. Again, typically we have a single wire analog input connection. So we have positive voltage going to the input device. Normally it needs some sort of power to create the actual analog signal. Then the input device feeds to the input module using its input terminal, and then you've got the 0-volt return. So that's quite straightforward, as we've seen before. With analog inputs, it's much more common to see a 2-wire input connection. So in this case, the input device itself has 2 wires. This reduces the amount of crosstalk on the module. It simplifies the connections for the user, but it also simplifies the internal electronics on the module as well. So this is typically what you'd see. The input module itself would have some sort of power connection to the positive voltage, and of course it would have the 0-volt return. And then on the input module, it would provide the positive power to the device. That eliminates the requirement for a terminal rail, of course reduces installation costs and panel spaces, as we've seen before, but it also simplifies then the connection of the input device itself, and then the wiring comes back to the input module. 2-wire may also include current sourcing. Current source is important because with a lot of these analog devices, they are providing a current by controlling a resistance, typically 250 milliamps. So by being able to source the current to the input device, that can simplify the way that that current is actually generated in the application. So it's quite common to see this current sourcing arrangement with a 2-wire system. although sometimes it's not strictly current sourcing, it's just voltage sourcing, and then it's up to the input device to convert that voltage into a current, again via resistor. But that's all. Some of that is fine terminology and some of it's not relevant. It will depend on the exact arrangements, and it depends on the input module itself. But certainly with 2 wires, yeah, this is quite a popular arrangement because it does reduce again the requirements for terminal rails. It also reduces the installation costs and panel space. And the additional idea here with that current sourcing, yeah, that can simplify how we get the energy out of the device. So that makes it more straightforward to implement as well. 3-wired analog input circuits are also common, same as before, except for now we have an additional 0-volt connection which is dedicated towards a shield. Now normally with 4 to 20 milliamps we don't need a shield because the way the wires are twisted together, any noise that's on one wire would also be received on the other wire and they would cancel out because of the twisted pair arrangement. But if you're using a voltage analog input, that's not the case, and then you probably need some sort of shielding. So a shield would cover the voltage wires and that would protect against any external influence. You can also use that with current as well, but again not so much required, but certainly you do require that with voltage inputs, certainly if you're going any sort of distance. So having 3 terminals, that just gives you the extra connection for your module right onto the input module itself, reduces any idea of noise being injected into the system, just makes it more reliable and more accurate. We also see 4-wire analog input connections. In this case we have 4 terminals on the input device. Again we have the positive supply and an input signal, and then we have additional plus and inputs and wires for reducing wiring offsets. The idea is, particularly in RTDs, but also in other circuits, what can happen is the wires themselves can affect the circuit. Certainly with an RTD, we're measuring temperature based on resistance. So if there's any additional resistance in the wire, that can affect our temperature reading. So what we do is we have additional wires which act as like an additional source to determine if there's any sort of offset on the actual wires we're using for the RTD calculation. And that just allows us to have a more accurate temperature detection. So not always required and quite rare in my experience, but it just means that you have these additional terminals, and some modules have that. So same benefits as before, reduces the amount of external additional wiring via terminal rails, reduces your installation costs and panel space, and in the case of RTDs, particularly important to improve the overall accuracy of the circuit. Let's move on to analog output devices. We've talked about these. These are a proportional output to a device used to control the machine or process. So that might be the speed reference to a VFD or a servo. It might be the position of a process valve to limit the flow. And again, with process valves, limiting the flow can have an effect on temperature or flow or pressure. It can even control level, of course. If you're filling a tank, then controlling the flow can affect the tank level and so on, or emptying a tank can do the same. So process valves, although that's one category of device, there could be multiple process values that you're affecting by controlling that valve position. So analog output signals, we take the circuit here, we have a voltage or current device wired to the PLC output terminal. Typically that output signal is fed from a DAC, a digital to analog converter. That takes the signal from the backplane and the PLC's data table and gives you a direct analog output in terms of either current or voltage. So you have the analog signal, the output terminal itself, and there needs to be a return as always to allow that current supply to come back to the power supply. A single wire analog output connection would look like this. I don't see this as being very common. Most analog outputs have more than one connection, which we'll come on to. But in this case, we've got a single terminal for the output device on the output module. And then that means the 0 volts must be provided externally, typically via a terminal rail, to allow the current return. In this case, we can use the definition of source. The output module is sourcing current or voltage from its own supply. So typically the output module would need its own connection, although that might be derived internally from the PLC electronics. But the output module is sourcing current to the output device. This is probably more common, a 2-wire analog output connection. You have 2 terminals for the output device on the output module itself. You have a signal output, which is to the output device, so that will be your voltage or current output, and then the return is handled by the output module itself. So again, the output module is sourcing the current or voltage. This eliminates the requirement for additional terminal rails, again reducing installation costs and panel space. And again, you may need a 24 volt and a 0 volt connection to the output module, but depending what the voltage or the current is, this is often generated inside the analog module itself using its own DAC module, and the DAC actually generates the relevant voltage or current itself. So you may or may not need that additional 24 volt and 0 connection. 3 wires is also possible. The same as on the analog input side, we can have 3 terminals for analog output. There would be the signal, return, and then an additional connection for shield. Again, not really required for 4 to 20 milliamps because the twisted pairs on 4 to 20 milliamps eliminate any spurious voltage caused by EMC and noise and so on, but quite common in voltage signals where you don't have that level of protection, so you do need a shield to protect against external noise. Analog I/O doesn't need as much protection as discrete I/O, although you may want to implement some protection. Typically, the analog module itself provides protection via its own internal device or optocoupler. So the ADC or the DAC is providing that electrical isolation, or there may be additional electrical isolation using the buffer circuits that are inside the analog module. You may want to provide a resistor to provide the minimum load. Rarely required, but some low load or high resistance output devices do require an additional resistor. You might want reverse voltage protection. That's normally to protect the actual output device itself. Rarely needed on analog input, although you do need to be careful because analog inputs often have a limited input range. Another option is, as well as reverse voltage protection, is a Zener diode, which can also be used to limit the overvoltage. But normally analog wires are wired separately to discrete, at least in an ideal world, so the chances of high voltages getting into the system are a lot less likely. And you can also have protection via a fuse or MCB. Fusing is common because the problem with an MCB is, they can impose additional resistance on the circuit, which can affect the circuit itself. Fuses, using a simple piece of wire, have less effect on the system. But this is the real challenge with analog I/O. As soon as you start putting additional devices on the analog I/O circuit, you're affecting the value and you're reducing the accuracy and performance of the analog circuit. So for example, diodes, you might have that 0.7 volt drop, which can affect circuits. That's not a problem with a current circuit, but it is a problem with voltage. If you put a voltage limiter like a Zener diode, not normally a problem, but you may have issues there if you go over voltage. The fuse or the MCB, again, you're adding resistance to the circuit, which can cause problems. Anytime you add a resistor itself, of course, you're adding issues as well. So normally the amount of protection you have on an analog circuit, you've got to offset that against, are you actually affecting the analog circuit and making changes to your reading? So a bit more complicated for protection on here. If you're really concerned with analog I/O protection, the best bet is probably go for isolated analog I/O, which costs more, but at least that way each circuit is individually protected. And the worst case is then if that circuit fails or is affected, you'd have to move your wires to a spare circuit or maybe replace the analog module if more than one circuit is affected. So there are some calculations we can use. These allow us to convert volts to currents to amps and so on. And these are the main calculations we use. So the first calculation is Ohm's law. So Ohm's, he decided or calculated that volts is equivalent to current times resistance. So for example, if you have an application where you have a 1 amp of current and a 1 ohm of resistance, you know that the voltage will be 1 volt because that's what the formula tells you. This can also be used in current applications for analog inputs. So for example, if you have a current of 20 milliamps, which is 0.02 amps, and you have a resistance of 250 ohms, that comes out at a voltage of 5 volts. So there's a direct relationship there, as we mentioned earlier, between the 4 to 20 milliamp signal and the 1 to 5 volt signal, because using a resistance of 250 ohms, then you get 5 volts is 20 milliamps. You can also use Ohm's law to calculate volts for other purposes, but often you know what the volts is, and more likely you want to calculate either current or resistance. So we can rearrange the formula, and for current, current is equivalent to resistance divided by volts, and resistance is equivalent to volts divided by current. So if you know what the volts is, typical circuits are 24 volts. If you want to calculate the current, you can do that from resistance, and if you want to calculate resistance, you can do that from the current. And that can also help you if you know that you've got a minimum resistance for a particular circuit. You can calculate what that resistance is based on the volts and the current, or you can calculate what the current is, and then you can work out what the additional resistance you need to be able to get to that minimum resistance required. So Ohm's law is a fundamental calculation relating volts to currents to resistor. Another fundamental calculation is power. So power is volts times current. So power is measured in watts. So again, a very simple calculation. If you had 1 volt and you had 1 amp, your power would be 1 watt. Another way of calculating that is you can also calculate power is volts squared divided by resistance. That will also give you the power. So again, if you know what the volts is and the resistance is, that can get you to power as well. And you can also work the other way. So if you want to know volts, you can divide power by current. And if you want to know current, you can divide power by volts. So very important for calculating resistors. Although the primary method you need to calculate the resistor is the resistance itself, the other aspect of the resistor is you need to know what power it can handle. So if you know what the volts is across the resistor, and you know what the current going through the resistor is, that can be used to calculate the power. So you can make sure your calculation is sufficient so that that resistor is big enough to survive whatever's going across it. And the reason for that is if you had a typical quarter watt resistor, in many 4 to 20 milliamp systems, there is enough power and voltage there to actually exceed the quarter watt value, and that's why many of these resistance inputs you actually see a half watt resistor. So physically it's a bigger resistor, so it can survive more heat, and the reason is the relationship between the voltage and the current just gives you more power, so you need that bigger resistor to account for that. You can also calculate current. If you know what the power is and you know what the volts is, you can calculate the current. So again, quite useful. If you know one parameter, you can use that to calculate other parameters. I see this a lot for power supplies, by the way, where some power supplies are calculated as watts, some power supplies are calculated as amps, and then the same with your consumption of energy on the devices. Some give you amps, some give you current. So by knowing what the voltage is, you can then regularize all of your different calculations. So regardless of whether you've got current or power, as long as you know what the volts is, you can then calculate the total power or the total current, regardless of whether you've only got a current or power signal. So again, very important calculations, particularly for calculating resistor sizes, but also for calculating power supply sizes, can also be used for calculating fuse values and so on. So lots of relevant applications for knowing what the power laws are. The final one there is root mean square, useful for AC circuits using sine waves. So if you know what the RMS voltage is, you can calculate that. If you know what the peak voltage is, you can calculate that. So RMS voltage is peak voltage times 0.707. Peak voltage is RMS times 1.414. So it might be useful for calculating the actual high level voltage you might see. So even though you've got a 230 volt signal, the actual maximum volts might be as high as 264 volts. So again, can help you with sizing of certain components and understanding what the actual maximum voltage might be on a signal. Another common calculation that you might have to perform is a voltage divider using resistors. This is very useful for reducing voltages. So for example, you might have a 24 volt input coming in, but you might want to convert that into a 0 to 10 volt signal. So by using 2 resistors, or possibly more, what you can do is you can calculate the output across one resistor based on the incoming voltage that's coming across both resistors. So we have the concept here using the circuit diagram. We've got V1 coming in, which is powered across R1 and R2 and down to 0 volts. And then we have V2 output, which is just across resistor 2. So what we've got here is a voltage divider, and we can calculate this by using the formula V2 equals V1 times R2 divided by both R1 and R2. Of course, the resistance of the output must be much higher than R1 plus R2, otherwise you've got another resistor in parallel with R2. But if you know what those resistor voltages are, values are, then you can do more complex calculations if you need it. But very good for dividing voltages. As I say, maybe you want to get a 10 volt signal from a 24 volt input, so you could calculate that, and you could use a variety of different resistor sizes to get to the right values. This would also mean you'd have to look at the voltages coming in. You might have to look at what the variability is depending on the actual resistance output. You might also need to calculate the power of those resistors. So your watts calculation comes in on this as well from the previous slide. So there might be a few more calculations you need to do. But I've had to do this several times in some more complicated circuits just to get reduced voltages. Note this isn't very good for high currents. This is only really for signal level voltages and currents. This wouldn't be useful, for example, for converting a mains voltage into a lower voltage. For that, you would normally use a transformer. And if you want to convert high power, again, the power across those resistors would be very, very high. They'd be very, very big. That the current effect might be problematic as well. So if you're converting DC voltages, then these days you would normally use a DC to DC converter. So for example, if you need a 12 volt supply for a module and you've got 24 volt input, using a resistance voltage divider like this isn't normally appropriate unless it's very low currents. So in that case, you'd use a voltage converter. So it would take a 24 volt DC input and give you a 12 volt output based on the electronics inside that power supply itself. So still useful, but again, only for signal level voltages and currents, not so useful for higher powered applications. So we'll finish off with terminology. AC is alternating current, and voltage is usually the root mean square or RMS value, which is 0.707 of the peak value. Current is measured in amperes, and this is the rating of the power supply, and it can also refer to the magnitude of electron flow through a cable. DC is direct current. A diode is an electronic device that restricts current flow in one direction. Earth or ground, and sometimes earth and ground can be different because you can have a safety earth and you can have an equipment ground which is used for other purposes like eliminating noise. They are the connection to the ground, and the reason it's called the ground or earth is it is literally earthed into the ground at some point. These are used for safety and also on some cables to reduce electrical noise, as we've mentioned. Frequency is the number of cycles per second in AC, so measured in hertz. Again, in Europe we see 50 hertz, in USA we see 60 hertz, in other countries it will vary, so check what AC current there is if you need to. A fuse, this is an electrical device designed to stop power current when the limit is exceeded. Typically it's just a piece of metal that burns through when that current is too high. It just gets too hot and melts. IC, that's an integrated circuit. Positive, this is the wire supplying the current or voltage. So this is the bit that you would normally attach your red wire to, red being the colour for positive. MCB or MCCB, these are miniature circuit breakers or moulded case circuit breakers. They're an electronic version of a fuse. A bit more complicated, but a bit more reliable. They can also be reset, which is a big advantage. And they generally have a longer life without any degradation. Nominal means the rated amount. So you might see a nominal value on a power supply, but you may need to check the actual amount because it might be higher or lower. So a nominal power supply value of 24 volts might have a tolerance against it. Maybe it's plus or minus half a volt or 0.5% even. So you'd have to check what the actual voltage is if you're really critical about your actual voltage supply. Power is the rate at which electrical energy is transferred by an electrical circuit, typically measured in watts or kilowatts. Kilowatts being K, kilo is 1000 watts. PSU, that's the acronym for a power supply unit. Resistance, this is the measure of opposition to flow of electricity, measured in ohms or using the Greek omega signal. RMS is root mean square. 0 volts, or the return, this is the negative or minus or 0 volt wire that carries the return current back to the source. Typically that's a black wire in modern electronic circuits. Transistor, this is an electronic device that switches a large current from a smaller one. Variable frequency drive, or VFD, this is a device that produces an output to a motor to control its speed, and I've got additional presentations that cover what VFDs look like and how they work and what you can do with them. And the final one here, voltage. Voltage is the supposed pressure from the power source that pushes the current through the system, and that's measured in volts. Higher volts means there's a higher pressure, and higher volts also mean that the system could be more dangerous. Remember, once we get above about 40 volts, then there is a risk of shock. And if we get to very high voltages, then you need to be extremely careful, because those voltages can easily go through your body and cause burns or stop your heart or cause other internal damage to your organs. So you need to be very careful of electrical safety. And this is why in the machinery directive, which came out, most voltages in electronic circuits now are 24 volts or less. 24 volts is a relatively safe voltage, and you're very unlikely to get an electrical shock from that. And if you were to get any sort of electrical shock, it would be low enough that it shouldn't cause long-lasting damage. Even so, you still have to be a bit careful. 24 volts can still cause enough of a voltage that you can get sparks, and that could cause explosions in certain atmospheres. It's also enough that you could cause a fire, but generally 24 volts is considered a safe voltage compared to those much higher voltages, which can be extremely dangerous.